This is the last video on series and local behavior as far as complex numbers are concerned, and we are looking at the Laurent series. Um, oh, that came out very French, but because Laurent is French, right? So the Laurent series is motivated as follows based on Taylor series, right? Taylor series expand functions as f of z equals summation from n equals 0 to infinity of an into z minus z naught raised to power n. This requires the function to be analytic at z naught. So, example, if f of z is equal to 1 over z is not defined, f of z rather equals 1 over z is not defined at z equals 0. So, no Taylor series exists for at z equals 0 for 1 over z. So to handle such cases, now we introduce the Laurent series. So the Laurent series has come to help us with what Taylor series could not do. Taylor series is very good for analytic functions, functions that are differentiable everywhere. But for functions that are not differentiable everywhere, like 1 over z, then we need the Laurent series to take care of that. So what exactly is this series about? A Laurent series is f of z equals summation from n equals minus infinity to infinity, a n z into z naught raised to power n. And it splits into f of z equals summation from n equals 0 to infinity, a n z minus z naught raised to power n, which is the Taylor series side of things, plus summation from n equals 1 to infinity of b sub n all over z minus z naught raised to power n. So in this case now, we have the Laurent series splitting into, so for Taylor series, right, it starts from 0 to infinity, but Laurent series starts from Laurent series is just like Taylor series that starts from minus infinity to infinity, basically, right? And then it can be split into an analytic part, which is the Taylor series part, plus a second part, which is the principal part for negative powers. Okay. And that is the essence of the Laurent series. So it helps to bridge the gap created by Taylor series. So talking about negative powers now, negative powers look like 1 over z minus z naught, 1 over z minus z naught squared, and so on and so forth. They describe behavior near singularities. Types of singularities can be things like no negative powers. That is, we have removable singularities, or finite negative powers where we can have a pole, or infinite negative powers where we have essential singularity. We're actually going to talk about poles and singularity and all that before we finish up with this playlist. So let's talk about an annulus. Annulus, talking about region of convergence. Before now, we're talking about disk and all that, you know. But in this case, when we talk about annulus, so a disk is something like this, where you have the Z naught here, and you have this, and this is the radius, right? This is a disk. But an annulus is something like this. You have this, and you have this. So it's more like you have a particular small radius, and then you have a bigger you have a radius that is the big one. So, and then this now comes out like, so it's a disc that is is it perforated, that a center of it is cut. Its center has been cut out. So Laurent series converge in a ring. So we have R1 less than Z minus Z naught less than R2. So this region is called an annulus. So that region is actually called an annulus. So unlike Taylor series for disk, Laurent series avoids singularities by converging between two radii. Okay, so it converges between two radii. So you have, this is one radius. Let's say this is radius 1 and this is a radius 2 now. So you have this here, but then you now have everything in the shaded region like this now. So that's the annulus we talk about. So Laurent series converge in a ring. So R1 is less than Z minus Z naught is less than R2. So example 1, if we want to expand f of z equals 1 over z, of course, we know the solution is as follows. F of z is 1 over z, which is z raised by minus 1. So the region will have to be z, 0 less than absolute value of z less than infinity. This is already a Laurent series with only negative powers in this case. So any Laurent series that obeys this condition, that absolute value of z is between 0 and infinity. All right. So we have that. For example, 2, we say f of z is 1 over 1 minus z. Using geometric series, we have 1 over 1 minus z, and that's summation from n equals 0 to infinity of z raised to power n. And this is valid for absolute value of z less than 1. That if you try to get the radius of convergence like that. So this has no negative powers. So you know we already saw the different possibilities. We have no negative powers removable. That's the case of 1 over 1 minus z. Then we can have finite negative powers, where you have a pole and infinite negative powers, which is an essential singularity. We go to example 3 now. So for example 3, we have this f of z. Uh, f of z is 1 over z into 1 over z into 1 minus z. So you can split this into partial fractions. So we have 1 over z into 1 minus z. If we do it in partial fractions, we get 1 over z plus 1 over 1 minus z. So if we expand this now, we have one part, which is the 1 over, which becomes like the geometric series. And then the final series is the 1 over z part, which is, so at the end of the day, 1 over z is 0 raised per minus 1 plus this one, and 1 plus z squared, and all of that. And then the region is such that we have 0 is less than absolute value of z less than 1, because for this one already, right, this is actually this converges for absolute value of z less than 1. Then we just have this other part holding it down with 0, that, like right here. Then we can have two regions too. So for two regions, we have we want to expand f of z equals 1 over z minus 1. So case 1, what if you have absolute value of z less than 1? So we can rewrite that as 1 over z minus 1, and that's equal to minus 1 minus 1 over 1 minus z. So if we switch this over, and if we expand that, we have minus summation from n equals 0 to infinity z raised to power n. That's like the negative of the exponential of the geometric series, actually. On the other hand, what if we do absolute value of for absolute value of z greater than 1? In that case, you have 1 over z minus 1, and that is, we can split out, we can have it as 1 over z multiplied by 1 over 1 minus 1 over z. So in this case, we have 1 over z waiting outside, and then we now have, so this 1 over 1 minus z now is like 1 over z raised to power n. And then we have everything together now becomes this 0 raised to power minus 1 and this 0 raised to power n. So summation from n equals 0 to infinity of 0 raised to power minus n plus 1. So finally, we have 0 raised to power minus 1, when n is 0. So 0 is per minus 1, 0 is per minus 2, and so on and so forth. So the key insight we get here is that the same function has different Laurent series depending on the region. So absolute value of z less than 1 means positive powers. Absolute value of z greater than 1 means negative powers, as you can see here already. And then of course we can show the actual, if it approximates 2 plus 0 j, right? The actual is, and we try to do that for 1 over z minus 1. The actual value is 1 on the real side of things and 0 on the imaginary side. And the approximation is 0.999, which is as good as 1, by the way. So that helps. So for example 5 now, we want to expand f of z equals 1 over z into z minus 2. So the singularities are, so when you equate this to 0, right, this function will not be defined at z equals 0 and z equals 2. So those are called the singularities. So then it means the possible regions will have to be absolute value of z lying between 0 and 2 and absolute value of z greater than 2. Those are possible regions in this case. And if we resolve this, if we express this as partial fractions, we end up having minus 1 over 2z plus 1 over 2 into z minus 2, like this. Um, I think I took care of partial fractions under basic calculus. You want to check that out. And I think, did I make another video where I actually talked about partial fractions? Possibly. So then you want to now expand. So for absolute value of z less than 2 now, you have 1 over z minus 2 to be minus 1 over 2 multiplied by 1 over 1 minus 0 raised by 2. So that's minus half into summation from n equals 0 to infinity of z over 2 raised to power n. And if we combine terms to get the Laurent, we can then combine the terms. So this is not like, yeah, we can combine terms to get the Laurent series, because this is not like minus 1 over 2. Yeah, I mean, we just have that going like that. In summary, we see that the Laurent series is summation from n equals minus infinity to infinity, an z minus z naught raised to power n. And the key ideas are that negative powers describe singularities, and then convergence occurs in an annulus. Same function can imply different expansions in different regions, and then the annulus is given as R1 less than absolute value of z minus z naught less than R2. So, and we have practice problems as we would usually have. So you want to check them out. You have question 1 to 10 here. Questions 1 to 10. And then you have questions 11 to 20. As usual, I'll solve two of them and I'll leave you to try your hands on the rest. So let's see what I have for you in this regard. So, we're talking about Laurent Series. Laurent Series. It's difficult for me to call the name the French way and then call series the English way. So that's why it's coming out like Laurent Series. Laurent series. Yeah, so I'm solving problem 5 and then problem 19. Problem 5 is to expand f of z equals 1 over z minus 1 about z equals 0 for absolute value of z greater than 1. Then question 19, that will require us to do some, uh, you know, partial fractions. Expand f of z equals 1 over z minus 1 into z minus 3 about z equals 0 in the region, absolute value of z, uh, line from between 1 and 3. So let's go ahead and do all that and bring it home. So problem 5, the duty is to expand f of z equals 1 over z minus 1 about z equals 0 for absolute value of z greater than 1. Okay, so step 1. Step 1, we need to rewrite the expression. Rewrite expression. So to rewrite the expression, we factor out z, right? Factor out z. So that means f of z now is equal to 1 over z into 1 minus 1 over z, like this. So that, this is the original expression, uh, 1 over z minus 1. So we do it in such a way that by the time if you expand, if you multiply out, you get the original expression. So z times 1 is z times 1 over z, you get it back. So we have that. That's step 1 right there. And step 2, want to use geometric series. Use geometric series. So here we use 1 over w, 1 over 1 minus w, which is summation from n equals 0 to infinity, w raised to power n, w raised to power n for absolute value of w less than 1. So here now, if we have w to be 1 over z, all right, if w is 1 over z, then we have this condition. We have the condition that absolute value of 1 over z is less than 1, which implies that absolute value of z is greater than 1. So that's the condition we are working with. So in that case, we can then go to step 3 where we expand. Step 3, we expand. So to expand now, we have f of z equals 1 over z, summation from n equals 0 to infinity of 1 over z raised to power n. So, and in step 4 now, we go for the final Laurent series. Step 4, final Laurent series. So f of z now is equal to summation from n equals 0 to infinity z raised to power minus n plus 1. Of course, this is the idea. This is the combination of 1 over z, and this is 1 over z raised to power n, right? So this is 1 over z raised to power 1, 1 over z raised to power n. That's 1 over z raised to power 1 plus n. So but if we take it as this, that'll be z raised to power minus n plus 1. And that's exactly what we have right here. And that's the final Laurent series. So f of z now is now, if you expand this now, when n is 0, you have z raised to power minus 1. When n is 1, we have z raised to power minus 2. When n is 2, you have minus z raised to power minus 3, and so on and so forth. That's all we have there. So in this case, region of convergence is absolute value of z greater than 1. And what are the key insights we have here? So key insight, or what's the key insight? Key insight here would be that Laurent series, this is a Laurent series with only negative powers, with only negative powers, then it describes it describes behavior far from the origin. Far, it describes behavior far from the origin. Far, it describes behavior far from the origin. Yeah, and that's question 5 for us. I think we already did that in the it's in the notes before now. So let's go to problem 19, which is totally new. Question 19. That's problem 19. So want to expand, want to expand f of z equals 1 over z minus 1, z minus 3 about z equals 0 in the region 1 is less than absolute value of z less than 3. So for step 1 now, we have step 1, partial fractions. So that is 1 over z minus 1 into z minus 3. So, of course, that's a over z minus 1 plus b over z minus 3. A over z minus 1 plus b over z minus 3. So, yeah, we can use the cover up method, right? We can, let's multiply through by the LCM. So that is 1 equals a into z minus 3 plus b into z minus 1. If you don't understand partial fractions, you can check my calculus playlist. There's a part the way I dealt with every possibility you can come across for partial fractions. That should be under integration of using partial fractions. So uh, if you set z to be 3, this part will cancel out. So we have 1 equals a into 3 minus 3, which will cancel out because 3 minus 3 is 0, plus b into 3 minus 1. So that means 1 is equal to 2b, and that implies that b is equal to 1 over 2, settled. So on the other hand, we can set b to be 1. We can set z to be 1, right? Because if we set z to be 1, b can go easily. So we then have 1 equals a into 1 minus 3 plus b into 1 minus 1. 1 minus 1 is 0, so that eliminates b. So we have 1 equals minus 2a. That implies that a is equal to minus 1 over 2. Very helpful to have that. So with that, we have that partial fraction sorted. So we then have 1 over z minus 1 now into z minus 3 is equal to a is minus 1 over 2 all over z minus 1. B is 1 over 2 all over z minus 3. So that means that we have minus 1 over 2 into z minus 1 here plus 1 over 2 into z minus 3. So with that in place, then we can say that f of z is equal to minus 1 over 2 into z minus 1 plus 1 over 2 into z minus 3. So that's we have taken care of that. Then the next thing we go for step 2. So step two, we have to expand each term. Expand each term. So we need to expand each term. So expand each term. So the first term is, of course, we have minus 1 over 2 already waiting outside. We know that 1 over z minus 1, we can say that's actually 1 over z into 1 over 1 minus 1 over z, like we've always done. So if that is the case, if we geometric series, use geometric series, we have that 1 over z minus 1 is the same thing as 1 over z summation from n equals 0 to infinity 1 over z raised power n. That's very close to what we did initially. The other problem, that's problem 9 or so. So that means we have summation from n equals 0 to infinity for z raised power minus n plus 1. And this is valid. This is valid when absolute value of z is greater than 1. That's the first term. For the second term, so second term is 1 over z minus 3. 1 over z minus 3. In this case, we can say 1 over z minus 3 is equal to, so if we switch it over, this is like minus 1 over 3 minus z. Okay? Minus 1. So we just switch this over and the sign changes. So we then have minus 1 over 3 into 1 over 1 minus z over 3. So we are factorizing 3 here from under that. So, and then we can rewrite. So we write it this way, right? And then if we expand that, we then have 1 over z minus 3 to be equal to minus 1 over 3, summation from n equals 0 to infinity for z over 3 raised power n. So following the same kind of, it's just like the kind of behavior here, 1 over z raised power n. So here to be z over 3 raised power n. So this is now valid. It's valid when the absolute value of z is less than 3 in this case. So now we need to combine results in step 3. So step 3, combine results. Combine results. So when we combine results, we have f of z equals minus 1 over 2. And for the first one, right? Uh, for the first one, we have minus 1 over 2, then the expansion we have is this summation z raised by minus n plus 1. And then for this other one, we have minus 1 over 3, summation for z over 3 raised power n. So if we combine the result now, we have minus 1 over 2 into z raised by minus 1 plus z raised by minus 2 plus z raised by minus 3, and so on and so forth. Then plus, okay, the other one now, we have so initially, right, we had, okay, let me see, what did we start with? Okay, we also have 1 over 2 here. But in addition to that 1 over 2, we now have minus 1 over 3. So it's like we have uh plus 1 over 2 into minus 1 over 3, right? Into okay, I think I have jumped, but it's okay. There's a step I need to write to make it right. Okay, before I come here, let me do this step first. So if you combine the result now, we have minus 1 over 2, summation from n equals 0 to infinity, z raised power minus n plus 1. Then all this now, plus the 1 over 2 we had before, and then minus 1 over 3 that we got later. Then summation from n equals 0 to infinity for z over 3 raised power n. So this can be like, this can then be minus 1 over 2, summation n equals 0 to infinity, z raised by minus n plus 1. minus 1 over 6 summation from n equals 0 raised power infinity z over 3 raised power n. So we can then expand all this. That will be minus 1 over 2, then z raised power minus 1 plus z raised power minus 2 plus z raised power minus 3, and so on. Z raised power minus 3, trying to, okay, plus all that. Z raised power minus 3 plus all that. Then minus 1 over 6 now into 1 plus z over 3 plus z squared over 3 squared plus all that. So in this case, the region of convergence, so region of convergence would have to be 1 less than the absolute value of z, less than 3, because 1 and 3 are the singularities. So the region of convergence has to be between the two of them. So what do we find here? Key insight. The key insight we find here is that number one, the first term has negative powers, and it is valid outside absolute value of z greater than 1. So it has negative powers like that. Then the second term has positive powers, positive powers, positive powers. So it has positive powers, and it is valid. Um, that's positive powers, and it is inside, valid inside absolute value of z less than 3. So, and together, it forms an annulus. So it's more like, okay, maybe I can try to, okay, let me say together, we have, together they form an annulus, where you have 1 to be less than absolute value of z less than 3. Then this is a classic example of a true, okay, something like this now. You have this and you have this. So the radius of this is, so R1 here is 1, and then you have this other one, R2 is 3. So that's that radius. But then you see, for this one now, for the first one we said um absolute value of z is greater than 1. So with this radius now, okay, yeah. So this is the radius. So you see that this is than 1, greater than 1. Okay. And then for the other one, it's inside, now less than 1. I mean, less than 3. So they now intersect. So then together they form this annulus like that. That's what we mean. So this is a classical example. This is one here. So this is a classic example of a true Laurent, true Laurent series in a ring region. True Laurent series in a ring region. Okay, so with that, we come to the end of series and local behavior. We still have I think we still have about 9 videos to complete the complex number series, except something else comes up and that'll make us extend it. Don't forget to try your hands on the this. You have the first 10, and then you have the last 10. And I've done two of them. I've done questions, questions five, right? I think I did five and then 19. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you haven't subscribed, it will do you a lot of good if you can subscribe. Why not go ahead right now and subscribe? Hit the notification bell also so you can always get alerted each time a new video is released. Having done that, you can become a member of this channel by clicking on join. When you click on join, you'll find you become a member and you can see some videos first before others see them, or you can see some videos exclusively, that others do not get to see. You can also ask for PDF copies of my notes for your personal use. We can hang out together, all either physically if you're in the same geographical location at any point in time, or online, if you if that is better, and we can discuss whatever interests you on my channel, be it mathematics, data analysis, data science, machine learning, scholarships, writing books, whatever interests you on this channel. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.